All right, well, let's go ahead and get started. I think for those of you who were at my talk yesterday, this should be a slightly more relaxed pace. We don't have quite as much ground to cover. Just a little bit about this statement. As I was working on this presentation, this came to mind because I think that if you were a shareholder in begin and end in C++ application code, your shares are about to drop seriously when ranges appear. So it's a little bit of a funny play on words, which isn't making anybody at 2:30 in the afternoon laugh just yet. Okay, a couple words about my experience with ranges. I started working on this a while ago. I got very interested in it as it was coming. So a couple of years ago, those of you who are in Aspen know we had a library in a week where we actually tried to generate some examples, example code for ranges, and that was because there was frustratingly little documentation in the version 3 implementation. So we had some pretty good success with that and actually managed to get some of that ported in. So if you go to the version 3, this is Eric Niebler's range implementation. If you go there, you'll see some of those examples in there. There's some others. I'll give you references at the end of the talk. Since that time, at the day job, we actually put ranges in production, even though that's not recommended. I'll tell you a little bit more as we go along about what we've actually done with it. And also since that time, I've participated in the Library Evolution and Library Working Group in the Standards Committee, looking at the One Ranges paper, which we'll talk about, and working on it, helping try and evaluate the wording and so forth as it went into the standards. So I've spent a fair amount of quality time reading this stuff. It doesn't mean I'm the world expert by any measure. I take the perspective much more of an application programmer who's trying to use ranges. So that's kind of the perspective you'll get in this talk. Okay, so this is how we sort now, right? Pretty straightforward, simple. We pass a begin iterator and end iterator, and it does what it needs to do. This is how you're going to sort with ranges. You're just going to pass this. This is all simple, very straightforward. A few less characters, although there's a little bit of cheating in my calculation. So we'll talk about that a little later.
Depends on the length of A.
Excuse me?
Depends on the length of A.
The comment is it depends on the length of A.
That's not a minor point. It might be a complicated function that gives you back an array. It might be something really nasty. And in the old format, you needed to write it twice.
I see. So the comment is that if you made A much longer, then you would have to write it twice, and that's a very good point. Next time I'll write it much longer. Yeah.
Mm-hmm. Like if A is a computed function that gives you back an array, I've seen people write it twice and get back different arrays and actual crashes.
Right, right.
Not just
So the comment is that there are real bugs that can occur if you have a function that's called there and you're returning a function and you end up with two different arrays because you have to do it with different actual begin end. Okay. So obviously we've wanted to write it this way for a long time. It's just been an inconvenience that we haven't been able to do that. Here's another example. Find if. So I've got a little lambda predicate here, and in the old way, again, I have begin end. And then in this case, because I'm getting an iterator back, I have to check the iterator and make sure. This code isn't really much different in ranges. It's pretty much the same. It's just that I'm going to use a range end here instead of begin end. And I'm going to explain a little bit more as we go along about the namespaces and so forth. But I guess the real thing here is that even when you look at this code, we've still got kind of a lot of overhead for the way we're actually doing this. And it turns out ranges really gives you a simpler way to express this that's even more compact. So here's the ranges way with a filter view. And in this particular case, I've got the collection. I construct a view with my lambda, and I immediately can just iterate directly over it. So that's even cleaner, even clearer, even simpler. Okay, I couldn't go 10 slides and not show you code. So let me tell you what I'm going to talk about. I'm definitely going to show you a lot of range code today. I have this idea that in a way it's hard to figure out sometimes how to program with something if you've never seen an example before. I think we all use examples as a way to figure out how to do things. So hopefully you'll see a lot of range code today and it'll feel much more comfortable. I think that there's no doubt that as we go forward, most of the code will start getting written with ranges and the SDL code will change just because of the simplicity and shortness. And I don't think we're going to see the full impact of this for a while because obviously what I'm going to show you today and I'm going to talk about a little bit today isn't necessarily that easy to utilize right this minute. Okay, so a couple key points that I want to make sure that you walk away with. Views versus ranges and how to use them. And I will mention projections on algorithms, which is something brand new and totally new. I probably should have put on here, there's a couple of new algorithms and some new things that you'll see that are also part of the package. So as I did yesterday, some things I will and won't do. I definitely will refer to the standard in a number of places here. And I'm definitely, today we should have plenty of time to take questions as we go along. If I can't figure something out, then we'll defer it and take it offline. And as I mentioned yesterday, I'm a human being. I'm undoubtedly going to get something wrong. I've tried to make this presentation as absolutely accurate as possible. I'm going to shorten namespaces, and as far as the accuracy is concerned, part of this is I don't think I have anything in this presentation other than maybe snippets from the standard that I didn't actually compile. And I'll tell you a little bit more about that. Specifically, the environments I'm using is Ubuntu Linux with a few different versions of GCC. So of course that limits, my knowledge of what might happen on other platforms and other places. And I'm typically using F-concepts. That turned out to be actually a bit of an issue in some cases. And typically the default here is the range v3 beta 1 branch. I'll tell you a little bit more about what that is and where to get it. Or Casey Carter's CMC STL2 is the other option. All right, so since this is before C++20 is shipped, what is the status? And I think Yoda pretty much summed it up. You're going to have to probably be a little bit patient, or you're going to have to be willing to accept the fact that you are going to run into some corner cases at the moment. So, okay, so let's talk a little bit about how we got here. The one ranges proposal, that's the 898 paper, is the primary paper that influences C++20. That paper was merged in 2018 after the San Diego meeting. So when you go and look at the working draft today, you'll see the results of that paper in the working draft. That was a 4+ year effort on the part of Eric and Casey Carter in part. So if you ever meet or talk to those guys, definitely give them some love for the work they've done. It's a lot of work. And there's not everything in C++20 is in those papers. There's been a series of follow-on papers that add additional algorithms, bring things in sync with other algorithm changes that were happening, and I'll talk about those a little bit today as well. There's some fixes and some cleanup. So there's other things that are still in flight that aren't quite in the working paper. So as far as C++20 is concerned, we're basically design complete. which means that there will be more papers in the July meeting that's in Cologne. And in that meeting, though, there will not be design changes. So there won't be new algorithms, new views, or any of that kind of thing coming into C++ 20 for ranges or anything else for that matter. The only case where there'll be any design changes is if some kind of significant bug is found in the next year before the final version of 20 ships. And I mentioned the two reference implementations. I said I expect the vendors to ship quickly as time goes on. I'm not as confident of that after having some conversations this week. So we'll see. I think it's clear that on the GCC side, they're a little bit ahead of things because they have concepts at least initially implemented. And so that gives them a little bit leg up. And as you'll see, this is really predicated on concepts. Okay, so one day you're preparing a presentation for Aspen and you're writing some code, and this seems like straightforward and obvious code, and it doesn't compile, and it gives you a weird error reference, and you're like, oh, what's with that? So then you try out more compilers, and you get no joy, and then you say to yourself, hey, I know, Godbolt has a whole ton of different options available to me. I'll just upload this little sample to Godbolt, and this will no doubt work, right? No. So the good news about Godbolt is Godbolt has online various versions of both the reference implementations for ranges, so that's very handy. You can definitely try things out there. But if you take that particular sample, which is linked there, and you go there, you'll find out that it fails in the exact same way. So this is how I learned that the beta 1 branch was actually the branch I needed to be using, because when I submitted issues, I got this response here. And so this is not the only case of this happening to me as I was preparing this presentation. It probably happened 4 or 5 times. Some were legitimate issues, some are not. And this isn't really a legitimate issue, but then also Godbolt doesn't have the beta 1 branch just yet. And somebody was telling me maybe how to make a pull request for this, so we'll see if I can get that to happen. So what about your other favorite reference, CPP reference? Okay, well, we've got that. Let's see if, does it actually work? I probably shouldn't try to go to that page, should I? I probably will screw up everything. I'll leave it alone. So if you go to that page, this is why I made a little bit of a snapshot. You'll see that the documentation on ranges is relatively sketchy at this point. There's some good stuff there, but a lot is missing. And they have a code example on this page, and if you try and compile it, this is the error that you get. And that's because they're using Wandbox or some other technology that doesn't actually have access to the ranges library at this point. So you're a little bit out on a limb here. You have to be able to tolerate that some of the tools you might use on a regular basis aren't necessarily going to be helpful to you. Okay. So with that, let's talk a little bit more about the basics of ranges. So there's really 4 key things with ranges. There's the range itself, which is something that you can iterate over at its most fundamental level. We have algorithms, range algorithms, which are just algorithms that take ranges instead of iterators. We have views, which are a kind of range that's sort of cheap and lazy. I mean, it's cheap to copy. That's what I meant to say anyway. And it's a little bit lazy. So it means it doesn't actually iterate immediately like an algorithm does, and we'll see that when we get there. And then we have range adapters, which aren't necessarily such an obvious thing, but this is the facility that lets you make ranges into views and do a lot of the nifty pipe operations and other things you might have seen if you've ever seen any ranges code before.
Is range something that can be iterated over?
Mm-hmm.
Specifically random access or one directional? Or?
Yeah, so the question is there a specific kind of iteration that's required? Is it random access? And the answer is no, and we'll get to see that a little bit later. You can have input ranges, output ranges, so you have the same kinds of things that you currently have with iterators, and there's specializations of the range concepts for those things. So mechanically, we basically have a new header in C++ 20, the ranges header, and we'll have a new set of namespaces here. One of the namespaces, the primary one, is ranges, so it's std : ranges now. And that's where all the algorithms and the view types are. And then you have the ranges views, and there's the adapters in there, and I'll show you kind of why that is. And then, that's kind of long to type, ranges view. So you can actually just say std view and get to the same place. So in this talk, you'll see a lot of code that shortens the whole thing down to RNG. It's also in part because I have two different implementations that I'm working with, and they actually have different namespaces in their implementations. So, of course, you're asking yourself, why didn't we just put this in std : and the answer is that these things, the range algorithms that we have, aren't just drop-in compatible. For a number of the different algorithms, the guarantees are changed, and so it would be very disconcerting if you were using an algorithm and suddenly its behavior changed. So for a backward compatibility point of view, it just wasn't possible. It's not just that the overloads have changed, which they have in many cases. And you'll see that there's some removal. Well, I don't have an example of this, but there are, in some cases, removed parameters. And so that makes signature compatibility very difficult. Okay, so I think there: a fair number of people who are unhappy with this particular decision because it means that to get to algorithms now, you have to type std : ranges, or you have to have a using namespace like RNG to get there, like you just used to type std : So it makes it longer, and that's a downside, but I think people will learn to live and adapt. So let's go back to that question of what's a range and dig into it a little bit more deeply. As we've talked about, it's an iterator pair, but one of the things that's a little different here now is that the end iterator doesn't have to be the same type. So in current STL algorithms, you have the same type, but now we have an idea called a sentinel, which can be a different type. As long as it is comparable to the iterator, that's the important thing. And that actually opens up some interesting possibilities for ranges that weren't possible with STL, including the idea of generated ranges or logically infinite ranges, which you might just take a sample of some part of the range instead of actually iterating the entire range. So, just as an example, in boost state time, there's actually a set of iterators that are not actually standard compliant, but they're iterators nonetheless that take a function and a start point, and when you iterate across that, you can iterate through, for example, weak calculations or other kinds of complicated calculations. And that's a sort of a generated range, would naturally fit into that idea of a generated range. So of course, iterators, things that have iterators like collections, strings, all the sequence containers in general, of course, are going to qualify as ranges. So essentially, if there's a begin and an end, it's going to be a range, because the begin and the end, of course, is going to give me an iterator back. So there's a lot of things, obviously, in the standard library today, array, vector, map, set, list, that all qualify in this case. Interestingly, some of the container adapters are not going to qualify because they don't have iteration. Some other things you might not think about will qualify, like file system directory iterator. some of the regex iterators, string view, and in C++20 there's a new view type called span, which I'll go over a little bit, and that is also a range. So of course, it's not just the the standard library we want to be able to use. We want to be able to use other things, and of course, because we're using begin end, I can take something like flatmap from Boost, which is its own collection, of course, and it provides begin end with compliant iterators, and it will work just fine with range code. So in this particular example, you see at the bottom there, after I've constructed the map and populated with a couple things, I basically reversed it and iterated over it, printing it out in reverse order. Yes?
I guess if this FM would be a logically infinite thing, then I wouldn't be able to reverse it, right? Or sort it.
So the comment is if it's a logically infinite thing, I shouldn't be able to reverse it, and I believe that would be the case, yes. And sort would be, yes, that would be another one that would be a problem. And I believe, it'd be interesting to look at that and see, but I think that might be specified somehow with respect to the concepts, because I think the sort might have to be either a contiguous or random access range, for example. And that kind of infinite range would not qualify. So this is Boost flat map. Just as an aside, for those of you who are not at my presentation yesterday, there will be a standard flat map as well in C++20 that's a little different than Boost flat map, but that would also work the same way, of course. So next we have range algorithms. They're very much exactly like the algorithms you know today. And one of the interesting things about algorithms, if you think about it, is that as soon as you call the algorithm, it immediately executes the function. And the iteration over the range is controlled entirely by the algorithm. You don't have really any control over it once you've initiated the algorithm. So as I mentioned, it's not a drop-in replacement. A couple different things. The return values in most cases I think have been changed. The Library Evolution Working Group was working on trying not to remove useful information from an algorithm when it could return. And I mentioned yesterday there was an example of things like remove if and so forth from list and forward list, where the current STL was not providing like the count of things that were removed. And in general, they've tried to live to that principle of not removing useful information that the algorithm can provide without any additional cost. Okay, so I said views are ranges with lazy evaluation. There's a little deeper than that. They don't own any of the elements. So if I go back a few slides here to this reverse view, this does not own any of the elements of the flat map here. It's just actually looking at it at the range, observing the range, if you will. And basically the copy and assignment are order one. It's essentially something that you can do at a very quick level. The lazy part of it is that the execution of computation is not actually immediate. It can be deferred, so you can set up a series of views in sequence, and then you can actually trigger the execution yourself through the program. So again, if we go back quickly, you can see here there's an explicit for loop that I'm using to trigger the walking through the actual range in the reverse view. And you'll see this some more too. So that's a very fundamental difference, and that's why views and ranges, even though views are ranges, have to be a little bit different. Yeah?
You mentioned non-owning. If you go back 2 slides to that one, does that mean if it would be dangerous to replace FM there, like RNG reverse view FM, if it was like a function that returned a map, if instead of fn it would be like call some function, parentheses, and I would give that to reverse view, that would be a bug.
So yeah, so the comment is that if I have a function that I call that would create a temporary collection, would that be a bug? I don't think it's going to be a bug because I think the lifetime will be okay. But we would have to do that to be sure.
I know.
We have a comment in the back.
I'm fairly sure that that would be a bug, but in ranges specifically, reverse view has, I think, a deleted constructor overload that says if you pass me an R value, I'm going to assume it's a temporary, and even though it may not be, and even though there are temporaries that aren't R values, you know, it's just gonna, so if you type exactly what you said, it won't compile.
Okay, so the comment in the back is that there's an explicitly deleted constructor for R value references. So in that case, it might not compile. And that's actually a great thing to try out for the next version of this presentation. Yeah, over here.
You say that all methods of ranges are ordered one?
Yeah. No, so sorry, views. Views, yeah.
Is that so for a filtered view where to compute begin you need to iterate to find the first element that matches?
Yeah, so the question is in a filter view, do you need to compute? Well, the actual calling of the lambda or the predicate function, I mean, obviously it's going to have whatever runtime that predicate function has. So if it has to do 100,000 comparisons, you know, but copy and assignment, for example, you can copy and assign views with no issue. That's the primary function that you're getting there for cheap. Yeah, more in the back.
Yeah,
He's going to help me here.
I think what the deal is that the operations on the view itself are constant time, so I can, like, as you say, copy and assign the view.
Yeah.
But if I were filtering on primes, then as I start plus-plussing my iterator, plus-plus takes longer and longer and longer.
Right.
But I'm not plus-plussing the view, I'm plus-plussing the iterator. You never said anything about the operations on the iterators.
Right. So the comment is the operations on the iterators might not be order one.
Well, you mentioned begin. Begin still is like for the first iterator.
So the construction of the view might have to take a long time.
The
I
construction
think this
of the first iterator. Of the view? Construction of the view?
Construction of the view is going to compute begin because once you've constructed it, then it's too late. You don't want begin to take a long time, so you have to cache the begin inside the iterator. And this is only because they made that stupid rule about like everything has to be O1. Like obviously you should compute begin, honestly.
Okay, so
Okay,
the
begin is computed right away. Then.
I think that's
the comment in the back is that it's likely that the begin is computed right at the beginning, so that could be more expensive depending on, especially in the filter case, what it actually has to traverse in terms of the underlying range. Okay, well, good experiments to try.
You say that views are not owning. Was there any effort is that respect to making the views non-copyable?
The question is there anything to not make them copy constructible? I don't think that, no, I think it's fine to copy them. So, and you'll actually see examples of that. Copy assign is fine. So you can send these around, and that's kind of the nice part, actually. And the same thing kind of with span, right, where it, you know, it's a sort of view, if you will, but it's not like the views that are in ranges. So span is a separate thing from the ranges proposal, but.
What I find in my experience is that if something is a reference naturally,
Mm-hmm.
then I find it very natural that it's not copyable, and then you use ampersand to make these pseudo copies, like const ampersand or auto ampersand ampersand.
Mm-hmm. So the comment is he finds that if something is naturally a reference, you make it non-copyable. But I think the point here was to make these views a semi-regular copyable type, which doesn't have any issues. So you can go back to passing by value. Okay, so let's go on. Range adapters. Range adapters create views from ranges, And so they're basically a utility to allow you to get access to a range as a view. And this is the thing that allows you to create the pipelines, the Unix or PowerShell type composition statements that you'll see. These are declared in ranges view namespace, and we'll show some examples later on of how this is actually utilized. So let's do one more filter view set of examples, and I want to show you the same example 3 times actually. So I'm just going to traverse through a range and throw out all the odd values here. So you'll notice in the first case here, I'm just constructing the filter view on the stack like I would a normal object, and I'm passing it the vector range and the lambda predicate function, and then I iterate through and everything's good. I've already shown you an example of doing it this other way, which is you're basically putting the predicate right, or putting the construction of the view right in the loop itself. Okay, so that's a second way to write it. That's the same constructor. It's not really any different. Here's a slightly different way. This is using the adapters I was just mentioning. So in this particular case, you can see that we're creating evens on the stack with an adapter, and that's where we get this range view filter. And you'll notice here, it's only the predicate. It's actually getting the range of the vector through the pipe operator there, and then the iteration is exactly the same. So what you'll find is there's a symmetry here of, a case where you have ranges : filter underscore view, and then you'll have ranges : view underscore filter. And it just omits the actual range that it's going to take in that case for the adapter. So you'll see that pattern over and over in the name. Yeah.
Silly question. Do we have something like IOTA so that I don't have to type in all these numbers for my test programs?
You do, actually.
Okay.
We'll get there. So the question is, do we have IOTA? And the answer is yes. Okay. Yeah.
I think there's a proposal somewhere to basically have traits on whatever is on the right-hand side, so that auto is deduced from the right-hand side of the assignment there, or the construction there. Would that affect how we use ranges?
So you're saying on the right-hand side of that line right there in
Yeah.
the center?
Then the third line. So auto events equal BI. The point is that this looks a lot like you're assigning to a value, right? And you're not.
Evens is an object, and it's exactly the same thing as doing this, except for that it's literally exactly the same as this.
It can be marked const, and if you really want to, you can put ampersand after
Yeah.
auto or double ampersand.
Yeah, that's what I mean. So if that proposal for auto is approved, and then ranges have some kind of value type associated with them, like a vector itself or some reason, then all these examples will have to change to something like auto, const, ampersand.
So okay, so I think if I'm understanding the question, what you're talking about is you would actually like the type on the left-hand side to actually be, for example, a container that would receive the results. Yeah, so that particular aspect of ranges, which is in the V3 version of ranges, and it's called ranges : 2, that did not make it. And so that will not be in C++ 20 as of today. There was a paper in Kona for that, and it did not garner enough support to do that. As I think I'm going to say later, I'm sure this is not the last set of ranges facilities that you're going to get in the C++ standard. I'm sure there's going to be more as time goes on. All right. So just wanted to mention briefly here that views and ranges aren't completely, or views and range algorithms are not completely separate things. You can put them together and utilize them together. So this is an example of doing that. where instead of using the range for loop, in this case I'm using the range for each. Of course, not every algorithm in ranges would be compatible with views depending on what it is. In this case, I'm using the drop while view, which basically says, while the predicate is true, skip over it, don't drop it out. Okay, so collections are not views, but they are ranges. I just pulled this out of the specification, range.view, so that the actual words in the standard would be clear. So this actually is kind of helpful. It kind of gives a set of examples, and it allows you to sort of consume exactly what it's saying. Okay. So I do have to bring up one controversial topic because I've already crossed over so many lines with this particular thing that I thought I better mention it before John Kalb comes and hunts me down. So there's some ideas floating around that we really shouldn't use for loops anymore, and that everything should be pretty much like this, thing I have over here, where we should call for each as an algorithm instead. But you're going to see me write for loops all over the place. And I find it interesting that the standard committee, even in C++20, continued to improve the range for loop if we weren't going to use ranges anymore, or weren't going to use fors anymore. So I think we can start that debate now. Unfortunately, John's not here to debate me right now, but I'm going to use for loops for the foreseeable future. And that was another bad joke in the afternoon. Yeah, the init statement is something new, so you can have an initialization statement before the range declaration, and then it'll be only in the scope of the for.
Like declaring
Mm-hmm. Yep. So here's what the ranges sections look like. Not going to spend too much time on this. I will mention things like range.access. If you're interested in making customized things with ranges, there's customization points in that particular section. The range requirements, define much more precisely, and we'll see a little bit of this because we're going to talk a little bit about the range concepts and so forth. The adapters we've talked about are in the end and so forth. There's actually a lot of really good information in the standard for ranges because, as we'll talk about later, ranges being the first thing that's specified with concepts probably has the most precise specification of any of the standard library that we have to date. All right, so let's dig into the algorithms in a little more detail, and then maybe we'll do a little bit of a survey. There was an interesting talk I watched a while back that went through every single STL algorithm. I think it was in an hour, maybe an hour and a half. And maybe we'll try that here with the range algorithms, we'll see. Or maybe not. So as I mentioned, they're going to be familiar. They're improved, specified with concepts. I think I said all that. So let's talk about projection parameters. This is something that's new, and it allows alternate form of predicate filtering that's independent of what you would normally be able to do. And this really comes from Sean Parent and the Adobe source libraries, if you're familiar with that library, and was actually in the very original range proposals, and there were a number of other papers that were submitted that do this. So what does it look like? Let's say I've got a structure like stuff here that has a couple of members. It has an IDX member, and maybe I don't want to use the standard less than associated with the entire object itself, but I want to only look at one field. In this particular case, what I can do is I can just put a predicate on that one field. So that's what I'm doing in the Lambda there. When I get back I can just do less on the IDX member. So that's what a projection is. So that allows you to do some more sophisticated filtering, sorting kinds of capabilities. All right, so here's the cheat sheet. of all the algorithms in ranges, except for it won't fit on the slide. And yeah, so there's a lot. It's pretty much all the STL algorithms and then a few new ones. So you think we're going to do them all? I don't think we're going to do them all. So let's go through a few examples and just let you take a look at some range code. Okay, so here's a few simple algorithms here for each on a string. I have a lambda. All I'm doing is iterating through the string and pushing it out. So I'm going to put out hello. On the second one here, I'm using the count algorithm to just count up how many things are 6. So that's just like the STL algorithm. And on the bottom here, we've got an is-sorted question, which is a relatively recent algorithm in STL, but now you can just ask it with a range. All right, here's that find if example again. I think I already told you how to do this better, so we won't dwell on that one. Here's a different kind of sort, a couple different kinds of sorts, and nothing exciting here except for that on the second version here, I've given it a different predicate, just like you could with an STL algorithm. So if you dig deep into the specifications of these algorithms, you'll see that they're very much like the STL.
What's up with the list example?
What about the list example?
Is it all n squared, or is there a specific...
Actually, so the question is, what's with the list example? And actually, it won't compile. So I was you're a good straight man, and I'll tell you why in a second. Go ahead back there. It won't compile because it doesn't have the ability to sort.
Iterate or random access iterator.
Right. That's right. It does not have random access. Yes.
So a couple of times now I've seen you use string array elements.
Uh-huh.
Generally speaking, will the ranges algorithm work with C-style arrays?
The question is, will the ranges algorithms work with C-style arrays? The answer, I think, is no. I have tried that, but I think if you wrap a span around it, that's all you need to do. And in fact, I believe I have a slide for that. So here's some min-max type examples. In this case, we're returning a value specifically from the algorithm in min-max. Over here on the min-max case, I'm actually able to use structured bindings here, which is nice. So I get some really nice clean code for calling min-max. What happened there? I think we have some slideware there. Here's a copy of if example. I've given you kind of the full headers here in this case, but basically we've got a couple of we've got a couple of lambdas here. One's a predicate, one's actually doing something. So I'm doing a range copy if with a back inserter with that particular predicate, and so I'm actually making a copy into another collection. Okay, so as mentioned, I'm not going to survey every algorithm. Hopefully everybody here is familiar with algorithms in general. You can go explore them yourself. But let's talk about a couple of new ones. There's a couple new algorithms called shift left and shift right. It turns out this one's a little bit unique in that we're actually getting this as an STL algorithm and a range algorithm. I think the statement of the library evolution group is that from here on out, there won't be any changes in the STL algorithms themselves. They'll all be range algorithms from here on out. So most of the future evolution will just be ranges. So this one's interesting. It moves the elements a fixed amount, either to the right or left. I guess depending on Whether that makes sense in a sequence right or left, but I guess that's some thought on it. So let's take a look at what it does. If I have a vector of 5 elements and I shift left by 2, and in this case I've shown you the STL version of it, what happens is I get an iterator back that points at the 4th element there, so 1 past where the shift was, and the 3, 4, 5 has been shifted to where 1, 2, 3 was. But interestingly enough, the size of this has not changed. So in fact, if I just iterate directly over this container, I'll actually get 3, 4, 5, 4, 5 out of it. Yes?
Are you going to need to have a 4 or 5 at the end, or it can be garbage?
No, the end is past the 5.
No, it's not garbage.
It's not garbage.
It's never garbage.
Yeah. So in this case, I call erase on the container with the iterator that I have an end, and then I can get 3, 4, 5 only. But if I don't call erase on it, then I actually still have the original elements in it. Yeah.
But is that guaranteed? Because like std remove makes the elements into moved from state. But in this case, I know for int it doesn't matter, but is it guaranteed that they are not moved from?
Yeah, so the question is it guaranteed that they're not moved from? And I think the answer is yes. We probably should double check it to make sure.
These are simple reasons.
Maybe Arthur knows.
You're asking whether shift left leaves the move from elements and move from state? It totally does. The move from state of int happens to be its old value.
It's actually doing move. Okay, so it's indeterminate then.
If you
Yeah.
just wanted to copy them down, you could just use the copy, probably.
So just
And if you wanted to rotate them, you could just rotate
So
them. In
then
this case, we're just,
the last 4 and 5 there are not guaranteed
they are guaranteed because they're ints.
because they are
Moving
ints.
out of an int leaves it untouched.
So I guess Arthur, the thing I don't understand is why. I guess it's the equivalent of calling remove is what it is, right? It's just remove with a shift is what you're saying, because the size of the container is still 5.
Yeah, it's like calling remove where your predicate just returns true twice and then false for the rest.
Yeah.
But that would be a weird predicate.
Okay.
The other reason is that you can implement shift left with swap only types, and then you can have
Yeah.
again.
The relationship between shift left, shift right, and rotate is the same as the relationship between std remove and partition.
Okay, so there's the synopsis. I won't dwell on that. I have a reference here. You can go look it up. The ranges version is not yet merged, but should be there hopefully after the Cologne meeting. So another new one that is also not yet in, but in flight, and we'll see if it makes it, is find last. Which if you look in Boost, it's called find backward. And if you look at every paper that's been submitted to the committee so far, it's called find backward. And I covered this yesterday, but I think one of the interesting things is it's surprisingly hard with reverse iterators to find the last element and do some certain operations. So that was the motivation behind this algorithm. And I won't dwell too much on it. I'm just going to make you aware that that's a new algorithm that's in 20, and there's some references here. Zach Lean wrote this proposal, so he's here at the conference. If you're interested in this, you can talk to him about it. Okay, let's talk a little bit more about views and view adapters details. So if we go back to looking at the standard a little bit, in range.object.adapter, you'll find this little piece of information. And this was kind of what we were actually talking about before when I gave you that filter view example. You'll see that the adapters themselves, there's either the range with the arguments, there's the arguments with the range, or the range with the pipe and the adapter with only the args. And those three things are basically equivalent. And that's exactly the example that I gave you before. So, as I was saying before, the adapters allow you to make a range into a view. So here's a little bit more sophisticated version of that. So I've got a vector of int again, and I've got a couple of lambda functions. In the one case, I have a filtering lambda. In the other case, I have a transformation of lambda. So I have a for loop up here where I have the range, which is the vector of int, and then through the adapters, I'm actually filtering and transforming the range, and then you'll see below there that I'm printing out what the results of that are. So it's filtered and squared by the time it gets down to the for loop. So you get 0, 4, and 16. Now, you can demonstrate for yourself that these two things are in fact equivalent. If you write this code range is equal, which is the algorithm equal, and you write that the two different ways, and so the first one is the piped collection version, if you will, and the other one is the parameter version, and indeed those are actually exactly the same. Yeah.
It's basically a repeat of my previous question. To reply to that, if it would not compile if vec int there was a temporary.
That's my understanding.
Yeah.
Same trick.
So the comment question was that it probably wouldn't compile if vecint was a temporary. Okay.
So if I take these two expressions and I use the is the same on them, then their types are the same.
So the question is, if I take these two expressions and I use is same to see if they're the same type, will the types be the same? Hold on to that thought. We'll get there. Actually, I'm gonna show you a little bit of what are the actual types that we're actually getting out of this thing in a few minutes. Okay, so another point that's made in the standard here is this is sort of the precedence ordering. These two things are equivalent, so it's more right to left than left to right in this particular case. So let's do something where we actually look at what's happening here. Because I'm kind of curious, right? I mean, I think we all think we know what this code is doing, right? But let's just confirm for ourselves that this is actually doing what we think it is. So now I've beefed the lambdas and the functions up here a little bit so that they print out every single time they get executed. So we'll see if anybody's awake. The question is, how many times does the transform execute and how many times does the for execute? Yeah, back here.
Those are the 6.
6, okay. Any others? Any other ideas?
The transform and the for, you said?
So it's annotated there, the transform and the for.
Both of them 3.
So I hear a consensus of 3, which is the correct answer. And the slide is actually wrong here on the even. It is actually 6 times. That was 0 based, and math is not apparently my best subject. So in this particular case, though, it's doing exactly what you're thinking it's doing. Okay, which is to say that it's short-circuiting when the filter, does not actually return true. It never actually calls the transform, right? Which is what you would expect. Now, I will tell you that this is an area where you have to be a little bit cautious because it is not a guarantee that in all of these kind of cases, the iterator won't be dereferenced. And I'll actually give you a reference to some cases where people have been surprised where they have a chain of filters like this where they get more dereferences than they expect. And that's by design. So, yes?
Is there any mechanism that is already in the library or can be an extension to the library where you have a series of transformations or filters and then you try to do some smart thing with them, like reorder them or rearrange them to make them efficient?
Yeah, so the question is there anything that allows you to tell if it would be more efficient. Just as an example, obviously, this one would be less efficient if we put transform first, right? Because we would now call that transform, 6 times essentially before we filtered it out. So the answer is, to my knowledge, there's nothing. You're gonna have to evaluate that on your own. Okay. So back to your question earlier about what are we actually getting here for types under the hood? Because, we're putting together a whole series of, these types, and it's a little opaque given that we're always writing auto something, whatever, and then just iterating over it. So it's all nice and good. But the real question is, what's really going on? So this first slide here is just a little bit of machinery that we're going to need to do this. And if you've not seen this trick before, you can go to the Stack Overflow link there. I've only shown you the GCC version of it because that's all I was using. There are versions for all the major compilers. But this just allows you to do a little trick in some code where you can actually use the decal type on the particular object itself and print it out. So that's what I've done here, and you can see at the top, and by the way, I've cleaned this up just a little bit. I've taken some useless std : colons and other useless things out of it to make it fit and be a little more obvious, but the vector basic string of char, that makes perfect sense, right? That's exactly what we would expect for the vector at the top. So now when we put a join view around that vector and construct it, what do we get? Well, we get join view of ref view, okay, interesting, of vector of basic string of char. So the ref view is a bit of machinery that is being utilized by ranges to turn your range, your collection, into an actual view, and the join view is the thing that's actually going to do the work. Okay, so now at the bottom, now I construct a take view, and that view is only going to give me a limited sample of these items out. And when I get that, then I get what I expect: take view around join view, around ref view, around basic string of char, vector of basic string of char. Okay, so we indeed are chaining up the type construction here when we're constructing views in this particular case. Join view, yeah, so I haven't introduced join view yet, but you'll see some more samples of that in a couple minutes. All right, so let's, so we got about 30 minutes left. I think we're doing okay on time, but we might need to speed up just a little bit. So a couple of view types that you should be aware of that are in the standard library. String view, is there anybody in the room that is not familiar with string view? Okay, good. So, because we don't really have that much time, so it's a C++ 17 thing. It's a wrapper around string types. It will play really nicely with ranges as you're doing things. So let's briefly talk about span. I did cover this yesterday, but I wanted to talk about it a little bit again today. It's a non-owning view over a contiguous sequence of objects. Again, cheap to copy because it's really a pointer and a size. And constant time complexity in header span in 20. Const expert ready. Here's some examples of how to construct it. It has constructors for the contiguous range collection types like vector array. And this was your question earlier. You'll see that bottom one, I've wrapped it around a C array. So kind of getting back to the question in the center of the room earlier, my opinion is that where this is really going to be valuable is in cases like this where you want to pass some sort of a range to do something with it, and you want to just be able to pass that by value cheaply. You know it's going to be easy to do. So in this case, I've constructed a vector event, and I've written this function called print reverse, which uses the reverse view, which you've seen about 5 times by now, and it just prints everything in reverse. You'll note that at the call point of print reverse, I just pass a collection, and the span is implicitly created. Yeah.
the span is basically a pair of random access iterators or a pair of bidirectional iterators. I guess it's random access.
So the question is a pair of random access or bidirectional iterators. It's going to be a random access iterator and a size, I think.
Oh.
So I think typically the span is a size, and you may know better than I do actually on that. Nope. Okay. So a couple more functions on span. You'll see span is a big class with a lot of functions. You'll have to go look at it. But in the case at the bottom there, I've actually subsetted the span to the first two elements before I passed it into print reverse, and then I took the last two elements and subsetted the span. As I mentioned, there's a lot of basic accessors. It's a very collection-like interface, begin, end, and so forth. So be aware of that type. In the reference section, I give you a reference to the current implementation that's out on GitHub that you can go use if you want.
I have a question about the previous slide, the password value. So reverse view there will take that by value inside the before reverse view.
So the question is, does reverse view taking it by value? I don't know what it's using there. I think it may just move it, but it doesn't matter whether it does. It's cheap to copy.
Yeah, it's taking the span by value, but span is reference type, so there's no copying going on.
I understand that, but just to know what it means.
Yeah, we'd have to look at the constructors to see.
Yeah. My point is that you are making the effort to pass by value pre-reverse, but if reverse view doesn't take by value, then
Well, yeah, but reverse view could copy it or it could move it. It doesn't, yeah. Because it's by value, it doesn't really matter what it does, right?
Yeah, my understanding is that the code doesn't going to be the same no matter what it does here, but
I know, I understand that.
inside the reverse view object, it will have a span of int object that it got by copying SI.
Sure.
But that span will still just have one iterator.
Okay, so the comment is that inside the reverse view, it'll have a copy of SI, which makes sense. More questions.
Well, I was gonna say, I mean, we do care, right, that it's not moved, because you can use the same view more than once, right? The view itself doesn't get consumed by passing it along, right? So if we were to move SI, that would mean that, like,
You couldn't use SI below in this
Yeah.
function. Yeah, you're right. Mhm. Yeah. All right, survey of views. So here's the cheat sheet for views. It's a little smaller, fortunately, than algorithms. I don't have an example of every single one of these, but I have an example of most of these. So there was a question earlier about IOTA. So there's an IOTA algorithm, but there's also an IOTA view. So you can construct it like this and iterate over it. In this set of examples, by the way, I have actually given you the reference from the standard about what the description of the view is. So for all of these, I think you have a short description, except for maybe one, which isn't actually in the working paper yet. So hopefully you'll find this a helpful reference when you're looking at these views later on. You won't have to go back to the standard 100 times like I had to do. So take view, you've seen an example of this. This just takes a fixed number of items from a range. A couple of simple examples there. The bottom example I put in just to demonstrate to you that, well, what if you try to take 10 elements out of a range that's only 5 wide? Well, that'll work just fine. It will just iterate the entire range and then you'll be done. So we were talking about join view earlier. So here's an example of join view with strings. So it's going to compress them all together. Interesting thing here is that you actually wind up with chars. And actually, I should have done my example of what the types actually turn out to be. But you basically get chars to iterate over here. instead of actually strings. So that's kind of an interesting side effect of this. So that's what a join view looks like. If you do it with different, you can do it with different types, of course.
It's so one that's flattened.
Yeah, it's a flattening capability, and split is the opposite, which I should have put right after join, but it's a couple slides down. These next couple are sort of utility views, I guess maybe would be one way to look at it. So an empty view, of course, is an empty view. It has nothing in it. So if you look at the size, or you use the empty algorithm from ranges to interrogate it, you'll find out it's 0. So in this particular case, you will never reach that output. So why might you want this? Well, you can imagine a case where maybe you're writing a function that's going to return a view of some sort, and there may be valid cases where the return value just needs to be empty. So this would be a way to actually create that. Single view is a similar sort of situation where you can put a single element into a view and then you can iterate over it. So I've done it a couple different ways here, one with a string and one with a integer. So here's that analog to join view, split view. In this case, again, we've actually just used a std string, and we've split on the space. And once again, to really get this all the way out, I have to drop down to characters to do it. So one of the interesting questions for me is how this is going to play ultimately with strings and other types when we start using these views. I haven't had enough time to really explore that fully. I'd be very curious if you took something like boost string algorithms and tried to rewrite them entirely in terms of views. I think that would be an interesting project for somebody to do. Reverse view, you've seen a ton of those. Transform view. Transform view is something that is going to apply a function that allows you to change the values. So, here I'm multiplying by 10. When I iterate over it, I get those results out. I think we saw a little bit of an example of drop while before. Here we've piped it together, and basically we drop while it's even, and then we take 2 of those and we get 3 and 5 out of this range. So this is another example of how it's lazy, right? Because the object after leading evens is constructed there, and no calculation happens at that point, right? There's nothing going on except for maybe the calculation of the end. Yeah.
Is it lazy for transform view? Like, so you give it a function and does some computation on the value. Is it lazy in that it doesn't actually do that computation until you access the element?
Yeah. So the question is transform view lazy as well? And unfortunately, so this is actually a valid example. So transform view here doesn't do any calculation at all until you drop into the for loop and you start actually processing through the range.
Would that mean, like, if you iterated it over it twice, would it possibly duplicate the function calls for each element?
The question is, if you iterate over it twice, would it duplicate the function call? And the answer is yes.
In general, can you do twice on the views?
Let me get him first, sorry.
Is drop while in the next slide. I'm not sure if it's a slide or my understanding of drop while. So basically, you say drop while it's even. So basically 6 is even, so drop that. 2 is even, drop that. 3 is not even. So basically, if I now take, shouldn't it take 3 and 4 rather than 3 and 5? Or?
Yeah, so the question is that should it not take 3 and 4? Well, I compiled and ran this code, so that's what it does. And to be honest with you, when I was looking at this, I was like, yeah, I think it should be 3 and 4, but I think the answer is that it's going to keep applying that predicate across the entire range. It doesn't stop applying it once you've satisfied it.
Drops all the evens, so that's the range, which is 3 and 5. And you take 3 and 5 and 7, you take 2 of those, which is just 3 and 5.
Filter. Yeah. Oh, that's really filter.
Yeah, it seems like the same as filter, but okay. So we got no, we had one over here. Oh no, he's okay. All right. So I think behind you, you were going to say something. Yeah.
I was follow up on his question. In general, can you use views twice?
So the question
Or
is,
do they burn themselves?
in general, can you use views twice, or do they burn themselves out?
It's a value, isn't it? I mean,
What?
you can do any operation on a view
Yeah.
in just an imperative.
It's a really good question, actually. If the state, and maybe Arthur knows off the top of his head, but I think the state, once you iterate it, is going to be at the end, right? So you would have to reinitialize it.
Well, yeah, it's not necessarily the
The view should be fine. The
But if the view has the iterator state within it, then you're not going to be able to reuse it.
If it doesn't, then wouldn't you just have a beginning and end that's implemented with the curtains, and the iterator itself is walking over this view. But the view itself has not knowing, like, I'm holding on to this thing. You can see my iterator. If you ask for begin again, you get a new begin, but it's still at the beginning of its view. It should be fine. But again,
All right.
If drop out, it's something different.
So
It may well be.
So we'll compile and run it. I think probably need to table questions on this one.
Sure.
And we can, if we've got time at the end, we can come back to it and have some more discussion, but I'd like to get through the rest of the presentation. Okay, so next section is a little bit of hint on range concepts. So I'll give you a little bit of preview. We're not going to go too deep, but just maybe to help you if you're actually taking a look at the standard and how it's specified. So a little bit of an overview here. I said before, ranges is specified in terms of concepts. It's the first C++ standard library to do that. The concept design was finally hammered out after a long period of time in the Palo Alto meeting, where a group of the committee members and others got together to discuss how to do it. I've given you a link here to the result of that meeting, which is 3351. And that really provides the base for the concepts in the language in the library that's in C++20. When you're reading the standard, what you'll see is that unlike all of the other things like types, concepts are actually in camel case in the standard. So that's your clue that that's actually a concept. And there's an entirely new section in the library for the concepts themselves, which is a whole nother talk, I'm sure, in and of itself. And actually, I believe I have some references. Andrew Sutton did a nice talk on all the concepts that are in C++20, which I encourage you to watch. So in terms of ranges, there's a few specific concepts. There's the range we've talked about extensively. Common range, which is an interesting variation on it. So we said that Sentinel and Iterator can be different now, but the common case actually is the collection with iterators that are the same type, and that's called a common range. We also mentioned that there's input ranges and output ranges. So those have exactly what you would expect, is they operate with input iterators. And so algorithms that don't work with input iterators won't work on an input range. So there's a few more here. A sized range is a range that, because of the nature of it, knows its size in constant time. You also have random access ranges, which are random access iterators, and contiguous ranges, which are contiguous iterators. And that's kind of a new concept, I think, the contiguous iterator, or more recent thinking. We've always had the random access ranges, but the contiguous range is a more modern thing.
Is that just a whole bunch of existing ranges?
So the question is, how is sized range checked? I'll show you a little bit. Basically, in concepts, you would specify the trait for the particular thing. Let me get a couple slides down and maybe it'll kind of be clearer. So there's also view concepts, a couple of them. We mentioned before that a view is obviously a range. So if you look at the actual construction of the view concept, you'll see that it leverages the range concept itself. So you can chain together the concepts. And it has the additional property that the constant time, move, and assignment and copy. And then there's a viewable range, and it just says that this is safe to be this range is safe to be convertible to a view. So let's look at an example here specifically. This is the definition of the filter view that we've looked at before. So you'll see there's a number of different concepts here. There's the first one in the template parameter itself, the input range, capital V. And then there's the indirect unary predicate. That comes out of the base set of concepts. And then you'll see this other syntax here, if you're not familiar with it, says requires view, which is also a concept. And then it says and is object V pred. So is object V is not a concept, that's a type trait. And that's just saying that this has to be an object type. Yes?
What is this operator? Is that a meta function or something?
Oh, the question is, what is the iterator T? That's another type trait that says that this is going to be an iterator type. So on the second line here, what you see is the definition of the input range itself. So you see template and then input range, and you'll see that it's a range of T and an input iterator with an iterator of T. So this is the way these are specified. And as I said, the things in camel case are the concepts. And then finally, when we get down below, we have this concept view. And you can see that relies on another concept, several other concepts, two other concepts, range and semi-regular. And then there's this other little flag over here called enable view. And this kind of goes to your question before. The enable view, again, is not a concept. It's a helper trait that says, oh, this thing is actually, it's a range, but we've also told the system that this is a view. Because there isn't another way to necessarily distinguish between what's a view and what's a range. Okay.
Why did filter view require? Filter view requires the input.
It requires the enable view to be true for it to actually be detected as a view. That's how it's actually separated. Okay, so I think we should probably move on so we can get to the end here. We got about 10 minutes left. I'm going to briefly talk about performance because I don't have anything scientific to say at this point in time. All I have is anecdotal observation. So let's talk about two aspects of performance. The first one is, what's the compile time like? And as I mentioned before, we've been using ranges in production for a while now, mostly with algorithms, and we haven't really formally measured it, but I can tell you that there's a lot of other libraries that we use that expand the compile time pretty dramatically, whereas I don't really see the stuff that we started using ranges code really change observably. That doesn't mean that's going to be the case everywhere and for every situation. So the second question is, does ranges slow down the runtime? And again, I don't think we know the answers to this fully yet, obviously, because we don't really have a full system. But so far from my anecdotal evidence is it hasn't made any difference. And I think from a theoretical point of view, it's sort of obviously not going to make much difference because really you're doing the same thing that the STL algorithms are already doing. You're just unpacking the begin and end in a slightly different location. Views may be more interesting. And I think on the one side, views might help you avoid writing code that naively copies things. But on the other hand, there may be some traps there, as we saw in chained, in the case of chained views that might be a little more surprising than we know. I would also mention that there are things like boost range and string algorithms that are range-based that have been around for a long time, and they're very fast. So dragons, I kind of hear some rumblings that maybe the concept of GCC isn't the fastest thing in the world at this point. Obviously, it's a very early implementation, so I don't know that we can really judge anything from that. And I've left you the references here to the examples that were going on in the bigger world. And I think my slide cut off here, but in any case, it's a case where you've piped together several views, and again, the behavior is a little surprising. Okay, that's the primary talk, but I have a few more things. I want to give you a whole list of resources. So it might take me a day to get these slides up on, up on the web, but I think hopefully you'll find them useful. So the reference implementations, here's how you get them. Pretty straightforward. Slide problems. Range examples. You can see some examples in the Range v3 GitHub. I also have a GitHub from the library in a week. It's just a slight bit dated at this point because I haven't gone through and adapted it specifically for C++20. There's things in Range v3 that are beyond what's in C++20, and I think some of the examples in there are beyond that. Working papers. So the latest draft standard 4.10, that's where a really good place to look at what's there. Most of the things were added by the one ranges proposal I discussed before. That paper is linked here. The standard library concepts, there's actually a separate paper for that, which Casey Carter and Eric Niebler also did in 2018. That's the link there. And the original ranges proposal from 2014 is the 4128 link, co-authored by Sean Parent and a number of other folks. This next slide is the most recent working papers. So there's a series of things, as I mentioned, that are in flight. Move-only views is one of them. The series of new algorithms, I think, is shift algorithms. But there's a whole series of other algorithms in the post-Kona set there on 1243. And I think I mentioned the Range 2 proposal that was rejected by LEWG. But you can go take a look at that. Maybe that will get resurrected at some point. As I said, that is in the Ranges v3 currently. Here's some links to projections on algorithms, why they might be useful. Reddit, ASL, Sean Parent's seasoning talk. Anybody not watch Sean Parent's seasoning talk? Yeah, well, you should probably watch it if you haven't. Videos and blogs. There's a nice talk from this very conference by Eric, really getting things kicked off with the effort to get to where we are today. And he does things with ranges that are way more sophisticated than what I've presented you today. And then Eric also has a CPPCon talk from 2015. Chris DeBoa, who is involved in some of the extensions to the ranges in some of the papers that I just give you, he wrote a nice blog post a little while back. There's many more. So there is a lot of information out there. One of the tricky things is the difference between what's actually in the standard and what's in the blogs and what's in the actual world. Here I've tried to make it as close as I can possibly to what's going to be in 20 based on what's in the working paper and what's in the current implementations. Span resources, you can go look that up. Couple of observations. I think I mostly made this, but I think ranges is clearly the building block for the future. The code is much better, and there's a last lame attempt at a joke because it's a begin, not an end. So thank you very much. So we have 5 minutes left, so we can go back, or do we want to just take a few general questions first and go back if we want?
What about actions? Are actions going to be included in?
Yeah, so the question is, what about actions? And actions are not in the standard at this moment. I don't know the answer to whether or not that's going to be something that's going to come down the line or not. Okay, first up here and then back here.
So you're saying you didn't believe that you would see, maybe I misheard you, you didn't foresee seeing performance differences between like iterative versions and range versions of the algorithm.
Right.
Yeah. So I mean, one of the big opportunities here should be like loop fusion should be a thing. So is that just, is there some reason I'm missing why that's not feasible, or just no compiler vendors are like, we don't think we're going to be able to get around to that particular optimization? Like,
Yeah, so the comment question is that loop fusion might make it somehow that the range algorithms would be more performant. Again, I feel like if you look under the hood of what's really going on there, it's all just calling begin and end. So I don't, and I think the compilers are demonstrably pretty good at unrolling that stuff today. In terms of like vectorizing the loop and that kind of thing, I think that's a totally different matter. So you had a question in the back? Yeah.
So why do we need spans if we have ranges?
Why do we need spans if we have ranges? Well, as mentioned, the requirements, I think, will not allow you to, for example, take that C array and just use range algorithm. In fact, I know for a fact that it doesn't compile, at least in the current implementations, because I did try that out at some point. And I believe that's going to be because I'm not exactly sure what it is that's causing that. I'd have to think about it and look into it. Maybe Arthur knows off the top of his head again.
I was going to say the answer is that span has a concrete type.
Oh, it doesn't have a begin and end. Yeah, it doesn't have begin and end. But span does, yeah. So that's the problem with the C array. Yeah, that makes perfect sense. That's right. So the comment is that you could have a begin end that's a free function. Yeah, I don't know. That's a good question. Front.
I'm trying to wrap my head around how would I use this, because I don't think that I can wrap my head around the implementation. And I was wondering if I had a set of numbers, and is there a magic incantation with the existing views where I say that I want to double every even number and keep in their position every odd number unchanged?
Oh, so the question is, can I double every even number and keep the rest the same? In that case, you would have to be writing back, and with views, that's not really going to be possible. You should be able to do that with the algorithms.
But transform is like function.
Yeah.
Is the algorithm you're looking for.
Yeah, so you could do a transform algorithm and write it back in.
You have to put your if statement inside the transform. You can't somehow combine a filter and the transform.
So the question is, can you combine a filter and a transform? But I believe the transform algorithm will allow you to give a predicate. So we would have to look to be sure, but I think you can do that. Arthur?
I would think that either you would provide a transform if action, or
there you go.
You would have a filter view to say, I just want to view the even numbers, and then to that you would apply the action double all of them.
Right.
So that
you can't write back. Is his problem, right? Like if you want to,
With a view, you can't, but with
right,
action, you
fine.
do.
Yeah.
He wants to write back into the original sequence. So I think
you
the
would apply an action to that view of the even numbers, right? I would think.
yeah, but we don't have actions.
So there's no way for views to mutate the array. I mean, they're view by design immutable, right?
Yeah. So Yeah. Span allows you to mutate things, but I don't think through the ranges views you're going to be able to do it. So we have 13 seconds left. We can go on for a little bit longer. Yeah.
I'm surprised how bullish you are on the performance aspects of this. I mean, you go to one slide on that, but like, I've never seen it. Like, I've never seen Garland manage to compile a ranges example. Like,
So the comment is, I'm surprised on your bullishness of the ability. Well, I'm not quite sure. I mean, if you're doing Eric Niebler scale ranges examples, yes, I concur you're not going to get it to compile. But I think it also comes back to what I was mentioning at the beginning, which is that the situation is there's a lot of elements in flight that are not compatible with each other at this point. So, for example, I had another problem, I believe it was with filter view. So I had to use CMC STL2 for all the filter view code because I think in the beta branch of ranges, there isn't the appropriate CTAD to make things work the way you expect them to work based on what the standard says. So as a result, it's in the one implementation, but it's not in the other implementation. And so if you just go on Godbolt and you try and play, and you don't even have, as we were talking yesterday, we don't even have the beta 1 branch there at the moment. So it's a little bit dicey. From the production point of view for what we're doing now, like I said, most of what we ended up doing, I think we probably have 2 or 3 view cases where we actually used views. Almost everything else is algorithms. In part, that's also a learning curve. I don't know about how anybody else in this room feels, but it took me a little bit of time to wrap my head around the idea of how to use the views and actually get stuff to compile. I couldn't just write views right off the box. Now, hopefully, given that you've seen this presentation and these examples, it'll be a little easier. But yeah, I mean, I gave that example of take view. It's like, this is the simplest possible view code you could write and it doesn't compile. So there was a definite case where I wanted to use a view in production code and I couldn't get it to compile with, of course, an older version of GCC and an even older version of Range v3. So
when I say I couldn't get it to compile, I don't mean I got a compiler error. I mean I got a 10-second timeout.
Okay, I see what you're saying. Yeah.
Well, that's what the timeout is.
Yeah.
If you're writing containers, should one worry about this or just having in a memory stream?
So the question is, if you're writing containers, should you worry about this? And the answer is absolutely. You should provide the necessary begin ends so that ranges will work and every one of your clients will be happy.
But don't you need to provide some kind of dot range function or something? It should work from begin end.
Yep. I showed you the example of Boost Flat Map, which is completely unmodified for ranges. It has no special changes in it for ranges at all.
There was still that constant time size that asked about how to possibly check something like that. There was the concept that.
Right, but like flat map's not going to have a constant time size.
Will containers be constructible for ranges or should they?
Yeah, so the question is, will containers be constructible for ranges? We're losing the room here. And the answer is, that's what that range 2 capability was, is to be able to just say, here I've got this, for example, a filtered view operation, and then I can say range 2 and construct a container from that. And it didn't quite make it. So you can do that in range v3. You can't do it in the standard for a little while. I'm sure it'll be rectified at some point. So there's other ways to do it, right? You can use an iterator inserter and so forth. Yes?
So one thing now of writing infinite containers in some sense?
Yeah. All right, I think we better call it. Thank you.